capture, good. Bop, beep, bop, beep, bop. Mic check, okay. Okay, and I think we're ready to go now, probably, finally. All right, hello. Hi, welcome to FWA 2023 Intro to DIY Electronics and Electrical Engineering. I'm Lauren. Hello. Yeah, so we're going to learn about electronics and DIY electrical engineering and all the good stuff in between. I hope y'all are prepared because this is a 2-hour panel. It's going to be long, but if you need to dip out, it's going to be recorded. And if you register to the Google form link on the app, and put your email in there, I'll email all y'all out the schematics, the PowerPoint slides, the recording, all other stuff. So, cool. All right. So, try to nerd snipe me. Please do. Actually, don't. I need to get through this panel. We can do that later. Hi. So, I'm Lauren. Hi. Hello. Nick, Lauren, either is good. I'm an embedded electronics engineer by trade. I do 3D printing, VR, cosplay stuff, electronics as a hobby. I love felines, canines, and protogens. Wolf with Tron lines. Contact info is at the very end. Audience participation is encouraged within limits. So if you have any questions or any comments at some point, please raise your hand and we will try to get to them. But we will have Q&A session at the midpoint and at the end. I tried to put in a good chunk of time at the end for a lot of Q&A and extra stuff. So yeah, as I said, it's going to be 2 hours long. If you need to dip out, it's recorded. I'll send it to you later. Okay, so why do you want to learn about electronics and electrical engineering? Or I'm just going to put it as shorthand as EE. Do you want to learn it for career? Do you want to become an electronics engineer? Do you want to get into academia and do like a master's degree or PhD or some other third thing? Do you want to do it for hobby or learn to repair your own electronics, which is also another sector of why folks want to learn, which is a very valid sector and just kind of a good skill to have. Or do you just want fancy fursuit blinking lights? That's what I thought. Or are you a protogen in need of repairs? Also valid. So, disclaimer, this presentation is a wide intro crash course into everything EE. There's so many subdisciplines here and cross-pollination with other engineering degrees that it is just a fractal of stuff that I won't cover here because it's just oodles of stuff. So, yeah, life's constantly learning new things. I'm still, even though I'm somewhat experienced, I'm still learning stuff all the time, so feel free to, all of this is still, there may be a couple of mistakes here and there throughout this presentation, so just be aware of that. Additionally, don't be evil with the stuff you learn from here. Do not build signal jammers. Do not build electroshock weapons. Do not build anything that can harm people, or I will find you, or report you. Finally, some aspects of EE, such as high voltage or playing with the mains grid, can and will kill you. Be responsible, be safe, be cognizant. Don't try this at home if you don't know what you're doing. Please don't try to plug a fork into the wall. I think y'all know that. I think y'all are responsible adults. Okay, so here's the full scope. Also, can everybody still see this? Is it readable? Okay. Let me know if it's not, and I can walk through it. Let me know if that gets too loud and you can't. A little bit? Sure, can do. Is that good? Cool. All right. So yeah, let me know if you can't hear me or you can't read it, and I will read it off. what we're going to cover in this presentation, underlying physics of electromagnetism. So we're going deep, within limits. Basic circuit theory, typical components, how they look on schematics and what they look in the real world, tools of the trade, soldering, desoldering demo, multimeter demo, oscilloscope demo, virtual oscilloscope demo, circuit analysis exercise, circuit simulator demo, full process of designing PCBs from start to finish, KiCad schematic capture and layout demo, further topic shoutouts, and miscellaneous Q&A. So, oh boy. For a really deep understanding, which honestly, unless you're doing this for career or academia, you don't have to know all of this deep stuff. You will need calculus, vector math, differential equations, those scare me, continuous and discrete time transforms, Fourier transform, Laplace transform, that's for going from frequency domain to time domain. That's way over what we need here. A good grasp of physics, a fairly good grasp of chemistry, and a few things more. Again, this is only if you're going into like it as a career or for academia purposes or research purposes. For now, we'll stick with the conceptual basics. So electromagnetism is one of the four forces of nature, alongside gravitational and the strong and weak nuclear forces. Classic electromagnetism, which you deal with every day, can be broken out into a few different equations, primarily Maxwell's equations, Coulomb's law, Lorentz force, Gauss's law, Faraday's law, and Ampere-Maxwell's law. You really don't have to worry about quantum stuff every day, like unless you're doing that for like really small itty-bitty stuff, and I'm talking like nanometer scale stuff, which at that point, why are you here? You're probably in a research lab somewhere, let's be honest. So yeah, most of this is going to be fine. So a quick formatting aside, when you're reading these slides, underlined letters are the variables, and bolded letters are the actual unit symbols. Okay, electrostatics. Electrostatics deal with the interaction between two charged particles, stationary particles, charged particles. All matter has a positive, negative, or neutral charge on it, or no charge on it, and said charge is measured in coulombs, or the elementary charge E. The elementary charge E is equal to the charge of one electron, a proton. Those are some numbers for you. You don't have to memorize those because those are easily Wikipedia'd. But that is the charge of an electron and the charge of a proton, really small, like 10 to the negative 19 coulombs in terms of charge. Neutrons have no charge, and non-ionized atoms have no charge to them as well. For a given space, a given closed space, no charge is moving into or out of that closed space. The amount of charge in that space remains constant. This is just general conservation mechanics, like conservation momentum, kind of plays along here as well. You've probably heard this in school already, is that like charges repel, opposites attract. The forces between two charged particles is governed by Coulomb's law, and it is stated as Q1 and Q2, and this is really simplified, are the actual charge magnitudes for each point charge, and R is the distance between them. And for point charges, you can just say it's the center of them. But in the real world, when you're dealing with charged objects, you're doing the distance between their surfaces. K is the Coulomb, Ke is the Coulomb constant, and this is just formulating out what are the forces in between them. So that's in newtons. Or the forces are in newtons, the charges are, as stated, in coulombs. R, the distance, is in meters, and Ke is in Newton meters squared over Coulomb squared. Electric fields. They are mathematical representations of lines of force in space. So E fields or electric fields are created by charged particles with the electric field lines pointing out from positive charges and into negative charges. Neutral matter, of course, doesn't interact with the electric field, and the electric field strength at any given point in space is measured by volts per meter or newtons per coulomb, representing the gradient of the E field. The electric field strength falls off with the inverse square law as distance from the charge, or Coulomb's law. The more lines of force there are that pass through a given area space, the denser the electric field flux is. Okay. Moving charges generate a magnetic field around them. Stationary charges cannot generate a magnetic field, except for spin. The direction and vector of the magnetic field is always perpendicular to the direction of the moving charge. So the good rule is always the right-hand rule, right-hand curl rule. So if you're using your thumb for the direction of positive charges, then how your fingers curl around your wrist, that's what the direction of the magnetic field will be pointing around that movement of positive charge. So that's Ampere's right-hand grip rule, or simply known as the right-hand rule. So, continue. Magnetostatics. So just like the electric field, the magnetic field, or the B field, has lines of force going out of it, which describe the direction of magnetic force. The north poles point away, south poles point in, and the field strength of that is in amps per second. This is just the gradient, or the strength of the B field. There's some additional info on what the measurements are for that in terms of field flux. It's easy to see these visual lines of force with iron filings. So there we go. Permanent magnets arise from spin. So the actual electrons in them spin up, and they generate their own little magnetic fields. And then if all the atoms in a given bulk material align, then they create a larger magnetic field around them. Nope. I can speak louder though. Yes. I can speak louder. Yeah. Yeah, let me know if I'm not speaking loud enough. So yeah, that's really, this is kind of just how stuff gets magnetized, is that everything is a little bit magnetic one way or the other, but it's all disorganized, so there's no net magnetic field to it. But when you magnetize something, all of their magnetic domains align, and you get a net uniform magnetic field. So another rule is the right-hand, well, another variant of the right-hand rule is using your index finger and your middle finger and your thumb, and it's just stating how moving charges both generate magnetic force, magnetic field, and are felt. They feel forces on them when exposed to an external magnetic field. So there's some additional math for you, but I won't subject y'all to that. That can be read later. This is just the Lorentz force law. So the complete Lorentz force law is when you include the electric field and the magnetic field on charged particles. So that's including both the parallel direction of the electric field on the charge, as well as the perpendicular force exerted on the charge. So the inverse is true for the Lorentz force, is a changing magnetic field, so think transformers, can exert forces on charges, even stationary charges. This is what's known as generating electromotive force, or voltage. This is the principle that electric motors, generators, and transformers operate under. So change in the magnetic field flux, or d phi b over delta t, generates or declares what the EMF in volts is. So basically, electricity and magnetism are two sides of the same coin here. And light itself is just little self-sustaining packets of the magnetic field and the electric field just interacting with each other as a light photon moves. But I've already subjected you a lot, and we're not an undergraduate physics course, so let's continue to something more real world. So conductors and insulators, perfect conductors, so superconductors, have zero electric field inside of them, resulting in zero electric resistance. Perfect insulator, which doesn't exist, completely opposes any movement of charge, and it's said to have infinite electrical resistance. Of course, all matter in the real world falls somewhere in between, as well as semiconductors especially, which we'll get into later. 1 second. So, most EEs, including myself, don't mess around and use Maxwell's equations and all that other previously covered stuff earlier in our day-to-day. What we do is circuit network analysis, because it's a lot more practical and a lot quicker to use. And this is more relevant to what y'all would do as well, if you wanted to do this for hobby. It's basically putting a few constraints on it, on your circuit, such that you can make a few assumptions. And by and large, you can safely roll with some of these assumptions that you're not getting like external interactions of magnetic fields on your circuit, and also that you're not operating at like really high frequencies or really high edge rates, because otherwise you'd have to deal with a lot more things. So, units. Volts, we've already talked about that. Electrical potential, measurement of electrical potential or electromotive force. The variable is V or U internationally, and that's equal to 1 volt is equal to 1 joule of energy required to move 1 coulomb of charge. Amperes or amps, unit of current movement, and think of it as charge carrier flow rate. The variable for that is I, and 1 amp is equal to 1 coulomb of charge moving every second, moving through 1 second. Ohms are just unit of electrical resistance. It is the opposition to current flow, and that is equal to 1 volt per 1 amp. This is Ohm's law. You've probably heard that. Watts, unit of power, energy consumption rate, and that's just 1 volt times 1 amp. Here's the full equation of different other units, SI units, and how they relate to ohms and really any other electrical unit. Farads. This is units of electrical capacitance. So this is stating how much charge you can put in a given area. It is 1 coulomb per 1 volt is the equation, and the variable is C, but F is the actual unit. Henrys. It's a unit of electrical inductance of a magnetic field, so you're storing magnetic charge, air quotes, and that's how much magnetic field lines you can store, and that's 1 Weber per 1 amp. But let's continue. So current flow is the opposite of electron flow. So whenever an EE is talking about current flow, they're talking about conventional current. So that's the movement of positive charges. And
Everybody's device is on silent.
No, that's this.
Yeah, there's also other devices.
Oh, okay, yeah. So yeah, whenever we talk about current in EE world, they're talking about movement of positive charges. Current flows from the highest positive voltage to the lowest negative voltage in a closed loop. So, continuing. A circuit node or net is just a region between all other terminals, component terminals. You can assume that net has zero resistance. A few laws that you also have to use when doing circuit analysis is Kirchhoff's current law. So any current flowing into a net must equal all the current flowing out of the net, which you can see by this diagram. It's just if these two current paths, I2 and I3, are flowing into this node, then I4 plus I1 must equal I3 plus I2. What's up?
So basically, it's like if you're filling a tub of water, you can't keep filling it up more and more and more, and you can't endlessly keep filling it, otherwise it's gonna combust. So it has to have an equal amount flowing out as flowing in.
Yes. It's more, it's more of just like conservation of charge too.
Yeah, that too.
Yeah. That analogy kind of works though. Yeah.
You don't use the term ingress
Kind of. Yeah. Usually, I mean, the water analogy here is no stranger. I usually refer to something flowing into and then flowing out. So, yeah, that applies. Yeah. Another Kirchhoff circuit rule is Kirchhoff's voltage law. And basically that just says all the sum of all voltages around a circuit must equal 0. So if you're starting at, like, say this is a 9-volt battery, 9 volts, you're flowing through the resistors, you're coming back, this must be equal to 0. It must be at 0 volts here, otherwise physics has broken down. Okay, so now for some components. Here's a list of components from the most basic passives to the most complex active parts. This is not an exhaustive list. There are oodles, there's fractals of different components out there. If you want to scare me, talk about memristors. Schematic symbols are on the left side of the slides, and what the part physically looks like is on the right side of the slides, mostly. Relevant equations are at the bottom of the slides, and there's 2 primary component packages when you're assembling components onto PCBs. There's through-hole components, and then there's surface mount components. The through-hole components, their legs go through the board, and surface mount components just sit on the board. Okay, voltage sources. So these are what are your sources of electromotive force to push current around. They can be direct current, DC, like battery or power supply, or they can be alternating current, where the direction of current flows back and forth, just like the mains grid. So these are some schematic symbols. So this is a multi-cell battery. This is an ideal DC voltage source. This is a single cell battery, 9-volt battery, of course, power supply, and also potato battery.
What would the LiPo batteries fall under in those categories? Does it depend on what?
It depends upon how many cells.
Okay, that's fair.
Yeah, because if you're talking like an 18650,
Yeah.
that's just a single cell.
Yeah.
Yeah.
So is there a different symbol if it's an alternating current power source?
Yes.
Direct current?
Yes. So if there's if it's a DC source, then you'll always have the plus sign or negative sign somewhere just to indicate that it's DC. If it's an alternating current source, it depends upon kind of the style of who's drawing the schematic, but most of the time I've seen it just drawn as this symbol, but you erase the plus and the minus, you put just like a little short sine wave in it. That's pretty typical. Or like AC. But the sine wave symbol is much more common. Okay, resistors. They resist slow electrical current. They are frequency independent, mostly. But for like hobby grade stuff, you don't have to worry about that. So here's some schematic symbols for them. This is the North American symbol, the little like squiggly line, and then for the Europeans, it's just a rectangular box. It's boring. I like the squiggles. What's up?
Resistors can be important for certain electronics depending on how much voltage that your electronic can take. If you have, like, let's say you have like a 9-volt LED line and you have a 15-volt battery, that's going to need some kind of resistor on it.
Yes. Yeah. You have to have that voltage drop somehow.
Yeah.
Yep. Potentiometers, so those are variable resistors. Thermistors, those are temperature sensitive resistors. They change their resistance in response to temperature. Photoresistors change their resistance in response to light levels. So here's some through-hole resistors, and the larger they are, the more wattage they can take. Here's some surface mount resistors, same thing. The larger they are, the more wattage, more power they can take. Here's a good, really nice wheel of equations just relating volts, current, volts, amps, power, and resistance. Okay, capacitors. So they hold charge and they store electrical potential energy as an electric field. So they also resist changes in voltage too. Blocks DC. Well, actually, I don't even have to air quote that. It's just it blocks DC and it passes AC because they're frequency dependent devices. So XC, this is the capacitor reactance. So you can think of this as capacitor resistance, and that one I'm going to actually use in air quotes because it's dealing with the complex plane, and we're not going to get into the complex plane right now. But what it's saying is, depending upon the frequency that's passing through the capacitor or being fed into it, its reactance will vary directly and proportionally to the frequency. So that way, like, if this frequency is really low, like say like 1 hertz, no matter capacitance, the reactance is going to be really high. So that's where the blocks DC passes AC comes from. If you have a really high frequency going into it, then it'll be effectively 0 ohms, or that's what the signal will see at the capacitor. Oh yeah, that's what I was talking about earlier. This symbol, the little squiggly sine wave symbol for alternating voltage source. Hi.
This is pretty ignorant, but I've never understood like what purpose of the capacitor serves. Like I know that it holds charge, but is it meant to be kind of for like if voltage is suddenly cut to the circuit, like it's meant to kind of use that out, or is it?
Yes.
Yeah, exactly.
Yeah.
So there's actually a lot of things you can do with capacitor.
Mm-hmm.
You can use it as a way, as like a diode for filtering out DC from AC.
Yeah, I got that.
You
Yep.
can also use it for filtering out specific frequencies.
Yep.
And you can also use it as a way of taking a pulse input, like an alternating current, and using it to balance out the peaks and pits to turn it into a DC output.
Yes.
So a lot of times you'll see a very large input capacitor on a power supply as well. There's also some other things that can be done with it. For example, you said you had in there. There are capacitors that have a charge, and then basically once the charge reaches a certain point, it acts as kind of an analog logic gate. Very early computers would depend on things like this, like the error recovery system in the Apollo computer was a capacitor, and every time an error came in, it would put a little bit of charge into the capacitor. But if you ever got that capacitor charged up too much, it would say something's gone horribly wrong, and it would start the whole thing.
Right.
Whack.
So it's like
I didn't know that. That's really cool.
There's a guy who's got a fascinating.
Is it Curious
where
Mark?
he takes apart a wheel.
Okay.
It never went into orbit, but it was a real lunar computer, and they're amazing. It's technology that is just so completely foreign to our games of work.
We'll have to talk about that later. Let's put a pin in that. So yeah, basically what he said in terms of just stabilizing the voltage going into a component, because it's just a little reservoir of charge. So if your voltage drops out, then for like a short bit, at least that component will, yeah.
It's good to have one, especially if you have a lot of LEDs running on the same battery.
Yes.
Because if your voltage is kind of iffy, then it'll still output that voltage to the LEDs, and you're not going to get like blackouts or flashing or anything like that.
Yes. Okay. Inductors. So they hold magnetic flux, and they store magnetic potential energy in them because they're just little solenoids. So remember when we were talking about the right-hand rule earlier? The reason that they're coils is that when you cumulatively add up all the, if you right-hand rule and additively add them all together, then you get one uniform magnetic field. And that's how you can store more magnetic flux or more magnetic potential energy. And alternatively, they generate, going back earlier to Faraday's law of induction, they generate current from magnetic fields if it's a time-varying magnetic field. And inversely to capacitors, they block AC but pass DC. And they resist changes in current, and they're also frequency dependent. So this is XL, this is inductor reactance in ohms, so just like the capacitor, it's like the inductor's resistance, and I'm putting that in air quotes, this complex length. So if the frequency is really low, like say 1 hertz, then XL is going to be really low, and thus at DC, the inductor will just look like a short or zero resistance. But at AC, the higher F is, your frequency in hertz, then the higher XL will be, and thus it will look like a really high value resistor.
Inductors can be very important, especially if you're working with audio, like voice modulators, because if you don't have it like very, very steady, it can cause some issues. Let's put that way.
Diodes. They're one-way valves, so current can only flow through them in one direction. There's asterisks to that because there's different types of diodes. So ideal diodes, they only allow voltage in one direction, and they have no voltage drop across them, and they can take infinite amount of current going through them, and they can take infinite amount of opposite voltage to them without breaking down. But we don't live in the ideal world, so you have normal silicon diodes, which are pretty close to ideal diodes, as I described. Schottky diodes, which are just a lower voltage drop, because when you pass current through a diode, there's going to be a voltage drop that develops across it. It's usually like 0.7 volts or smaller, if there's like a Schottky. Some of them are designed to break down so if you apply opposite voltage to it, so normally you would apply, if you were forward biasing these across their anode to their cathode, current would flow. But if you put it in the opposite way of the positive voltage being at the cathode and then at the anode, at some point the diode would break down, and that's at a really high voltage, or for Zener diodes, that's at a specified voltage that's much lower. What's up?
So I'm a science ideal specifically with file systems, file layer, and from time to time we get these reports coming in from like edge or code locations where it's like a physical level, all a OSI level 1 physical level system though.
Yeah.
I say that this has to do with the like embedded system, embedded programming. Is this kind of where that realm of physics comes into kind of those hardware cards?
Yeah, because OSI is your physical layer. Yes. Or OSI level 1 is your physical layer. Yes. So that, yeah, I mean, that's in the realm. If you have an OSI level 1 failure, then yeah, something at the electronics layer has failed. Yeah.
Okay. I've always wondered actually like what that was actually entailed, but I just never see that explanation.
Yeah. Oh crap. We'll do that at the midpoint. I'm sorry. A lot of subcategories here for the different diodes. Usually made of 2 pieces of semiconductor material, one slightly positive and one slightly negative. So this is what the what is called a p-n junction. So it's just normal piece of silicon, but what you call doping with like boron or phosphorus to make one slightly more positive and the other one slightly more negative. So it provides holes, which are positive charges, or provides electrons. And the point here is when you forward bias it to get current flowing in one direction, then the positive charges and the negative charges come together, or holes come together, and the depletion layer between them shrinks, so that way you can actually get current flow. But when you have it in the reverse bias, as it's called, then the depletion region expands and you can't get current flow, just because there's opposition of charge in that region. So that's how p-n junctions work from a really high level. So let's pause for a second, because I completely forgot to do something incredibly important to do the random drawing for the soldering irons. So, un momento. 1 through 50. Huh? You registered on the Google form link on the app. Who here hasn't done that yet? Okay, tell you what, for all y'all who haven't, we'll continue with the slides, do it, and then we'll come back. Okay, what's up?
If you do, for a beginner soldering iron, or like a small soldering iron, if you have something like that, I highly recommend, especially if you have a suit that's coated with LEDs, bring those to your comms. Because the thing is that you have no idea what's going to happen, especially with fursuits when you're moving so much. The seams between the wires can snap, and they can cause issues.
Yep. So, okay. So LEDs and photodiodes. They're still the same as diodes normally, but they will emit light when you pass current through them in the forward bias. Or with photodiodes, they will actually generate current when you shine light on them. Photodiodes are basically just small little solar cells. That's all they are. So this is kind of just the overall band structure of how it works is there's a band gap, what's called, of amount of energy that's required for electrons to start moving across the p-n junction. And that's got to be equal to the amount of energy in the light that is shining upon it to make that jump. And if the light is too weak in terms of wavelength, or not enough energy in terms of wavelength, then it won't actually start conducting current. Okay, bipolar junction transistors. So they are electronically controlled switches, and they are current controlled. So that means that one of their pins, called the base pin, you have to inject current into it to get it to start turning on. And their output current across the collector current is proportional to the base current. And that proportionality constant is called HFE or beta. That's its gain factor. You also have to, there we go. Don't know why that didn't show up. You also have to meet a minimum turn-on voltage of 0.7 volts before they start operating across their base and emitter pins, or negative 0.7 volts for PNP. So, yes. What's up?
Junction transistors are also pretty important when it comes to audio. It depends on exactly how much you want to amplify your current or change it, but if you need to make those changes, then these can be very important. So make sure you don't forget them.
Yep. Yeah. How are we doing so far? Any questions? What's up?
So are these related to or completely different? Never mind, I answered my question.
Okay. I saw somebody else's hand up back there. No? Okay. All right. Field effects transistors, or MOSFETs. They are electronically controlled switches. They are voltage controlled. So unlike bipolar junction transistors, which you have to feed current into them, MOSFETs, or FETs in general, you don't have to. They are purely voltage controlled on their inputs, which is really good if you don't want to have to feed current into your transistor to get it working. So that's really good. And the reason why all of our modern electronics are such low power is that they're all MOSFETs, because you don't have to spend current putting into the transistor to get it to operate. It's very little current compared to a bipolar junction transistor. So their gate input, which is the analogous pin to a base pin, is isolated from the drain and source pins, which are the MOSFET analogs of your emitter and collector pins, or your output pins. Okay. Okay. Integrated circuits. So integrated circuits are all the previous components and more. They're all packaged together. Why is that? There we go. Okay. They are all packaged together for a specific purpose, built into just larger circuits, but in one small package. So audio amps, clocks, op amps, logic gates, video generators, memory, radio transceivers, voltage regulators, the list goes on. Here's a few schematic symbols for them. So like logic gates, op amps, and voltage regulators, 555 timer. For hobbyists, y'all will know and love this thing. And here's a few packages. For most of y'all, especially if you're getting started, you're going to be using through-hole parts, so the div package is what you're going to be extremely familiar with. But as you build your skills, then you can start to use some of these other parts. And once you get up to VGA level, then you're already basically a pro. What's up?
When it comes to integrated circuits, depending on the circuit, it can be programmed to do different things depending on your application. A good example of these is like, let's say you want LEDs that are time reactive, LEDs that are music reactive, things like that. Those can be important.
And that's what microcontrollers and microprocessors are, is that they're integrated circuits that are programmable intentionally, or FPGAs, which are also programmable.
It's different from like, my Raspberry Pi, or kids, buy some similar or is that basically what they are?
So the chip at the little silver square on the actual board of the Raspberry Pi, that's a microprocessor.
Yeah.
It's a
Okay.
it's a system on a chip.
Oh, so this is even like a small package.
Yeah, I mean this still covers that.
Okay.
It's just a lot more peripherals added on to it.
Okay.
Yeah, so that the chip on the Raspberry Pi is called the system on a chip because it's not only a microprocessor, but it's also your memory, it's also your graphics chip, everything just kind of crammed together. So there's still relations there, where
That chip there on the top right, I believe that's an ATmega 328.
it is.
That's on an Arduino Uno.
Yes.
Yeah.
Okay.
Yep. Yeah, y'all will really, as y'all play around with electronics as a hobby, you'll get familiar and you'll be seeing that ATmega 328P everywhere. It's pretty universal for hobbyists. Okay. So additional basic equations, Ohm's law. So as we talked about earlier, voltage equals current times resistance, and play around with the algebra there, and you can figure out whatever you need with whatever input you have. Power, so that's watts equals volts times amps. The charge equation, which basically states if you know the capacitance of a capacitor and you know how much voltage you've applied across it, then you can figure out how much actual charge in coulombs you've put into it. And if you recall earlier, when I was talking about capacitors and inductors, in terms of like their resist changes in voltage or resist changes in current for those two, this is what I'm talking about for these two equations, is that capacitors, they want to keep the voltage across them about the same. So whenever you, any delta V or change in voltage over change in time for a given capacitor, it requires X amount of, or I amount of current to do that. Inductors themselves, they want to keep the same amount of current flowing through them. So that's why whenever, say back EMF, whenever you have current flowing through an inductor and you suddenly stop that flow of current, like say through a motor, then the voltage will suddenly spike because it's had this inertia of current flowing through the inductor that once you just stop that, it'll suddenly develop this large voltage across it. Okay, so passive resistor component combination equations. So are we all familiar with concepts of series and parallel? Raise your hand if you don't. No? Okay. Series is components just strung together like a chain, and in parallel, they're put together side by side in parallel. So here's the equations for resistors. In series, you just sum their values together, but in parallel, you sum them by their reciprocal. So say if you have R1 and R2 in parallel, their equivalent resistance in parallel is 1 over R1 plus 1 over R2, and then 1 over all of that to give you the final total resistance. And for capacitors, this is opposite. If they're in parallel, you just sum them together, normal sum. But if they're in series, you sum by reciprocal. So 1 over C1, say if you have two capacitors, C1 and C2, 1 over C1 plus 1 over C2, and then 1 over everything gives you the total capacitance. Inductor combinations. So in series, you just sum them together. They're like resistors in how the combinations work out to them. But in parallel, they're again like resistors. You just sum by reciprocal. So if you have L1 and L2 for inductors L1 and L2, if they're in parallel, just 1 over L1 plus 1 over L2, and then 1 over everything gives you the total inductance. Okay. Some active component equations, which you don't really have to know. Like, well, this one you don't really have to know because you can just read off the data sheet. But this one will be relevant for y'all if you play around with BJTs. As I talked about earlier, BJTs, they have a gain factor to them called beta or HFE. So the amount of current flowing out of their emitters, there we go, is equal to the base current that you inject into them, plus the collector current flowing through them as well. So currents flowing from the base to the emitter and also from the collector to the emitter. And the amount of collector current that flows is equal to the HFE or beta times your base current. So that one will be relevant if y'all are going to play with BJTs. Okay, before we move to the demo, has everybody registered on the Google form? Going once, going twice? Okay, let's raffle. Let's raffle real quick. Okay. And let me pause this. Let's continue. Okay. All right. Let's go second. Who is our second winner? 69. Nice. Nice. Please be here. Please be. Siegfried? Nice. We love the funny number.
Thank you.
Okay. 18. Who's 18? Brendan Brady. Can't believe we got friggin' 69. Good, good. Okay. Let's continue. Because now is a good time that I did all that, because I'm going to give you all the soldering demo. Okay, cool. So, for most EE work, the two most common tools you'll be using are a multimeter and a soldering iron. Sorry. My AVE got out for a little bit. So the multimeters, you use them to probe for voltages, currents, resistances, capacitances, and so much more depending upon the features. And then soldering irons and also reflow stations, which use hot air, are what you use for soldering and desoldering. So that you just melt the solder to the component which you attach to the board. So that's both making a mechanical connection and an electrical connection. Okay. Reflow part, or the reflow iron, you generally only use for surface mount parts. Additional tools that will be relevant for repair and just general work are wire cutters and strippers, tweezers, needle nose pliers, anti-static mats, and anti-static straps, because you don't want to be zapping your electronics while you're trying to repair them. There we go. Strap. Also, don't get wireless anti-static straps. Please don't fall for that. Please don't fall for that. You need a path for the charge to dissipate through, and it can't just be through the ether. Additionally, iFixit kits. I'm not sponsored. These are really friggin' good. Go to Micro Center. If y'all are out of town, go to Micro Center. Pick yourself up an iFixit kit while you're here. Again, not sponsored. They're just really good. No, I don't want to be sponsored by them. Okay. Now, yes. Answer. You can't really. Okay, unless you're buying the bargainist bin of bargain bins, that works. Thank you. You can't electrocute yourself with a soldering iron. You can burn yourself with a soldering iron. Yeah. Yeah. Yes. 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 Answer in the back and then I'll get you. So, using butane irons for soldering is really only good for like really large components, or if you're doing heat shrinking. Because otherwise you can easily torch parts. Most of the time you're going to want to be using electric fine tip soldering irons. Well, sorry, because I got to think that you can get like fine tip butane torches that blow the hot butane exhaust onto the tip, but again, you're kind of risking the components with like collateral hot exhaust and hot gas from that. So yeah, you have a lot less control of compared to an electric one, which is digitally temperature controlled. Really, just go with an electric iron. Can't go wrong. Yeah, like big wiring assemblies, butane torches are fine. But if you're doing like small electronics, you're going to be using an electric iron. Yep. Yes.
So quick safety tips. If you are making any electronics for a fursuit, make sure everything is waterproof as much as possible.
Mm-hmm.
And then secondly, when it comes to using a soldering iron, I made this mistake myself. Do not call me stupid, please. When it comes to using a soldering iron, make sure that even if it's even slightly close to anything flammable, that it is not close to anything flammable, because it will light something flammable on fire. Because as much as you hate to say it, things will radiate heat, especially if they are damaged, and they will catch things on fire if they're too close.
So, answer. So we are not an After Dark panel.
We are not an After Dark panel. Yeah.
Yes. What? Just the luck for this panel. We hit 69 and then we're talking about E-stems. Just the luck. We can talk about that one-on-one later. So, all right. So, for this soldering, can y'all see this, by the way? Let me see if I can enhance.
Oh yeah, right-click and projector on OBS.
Right-click the display and then hit.
Full screen projector preview. Excellent. Thank you. Thank you. I'm still a little bit of a noob at OBS. All right. So for this year's for the soldering demo, we're going to use my copy of last year's FWA 2022 Compass ConBadge that I made for last year's panel. I don't have any more of these, I'm sorry, but I do have the files up on GitHub if you want to make your own. So we're gonna get tweezers, and before I even touch the board, get strapped in, make sure that the anti-static strap is nice and good, make sure you're well grounded, make sure your work surface is clean. Yes. All right. So, we're gonna do like a, yes. Hi. Yeah. So what we're gonna kind of do here is, I can't really zoom in because I don't have a USB microscope. I've just got my camera. But we're gonna do like a really mock repair job. Say that one of these, so we have these through-hole pins down the side of the badge that I designed them such that you can plug it into a breadboard. Let's say that the soldering joints on these have gone cold, and you can tell that they've gone cold if they're no longer silvery and somewhat reflective. If they've gone like dull, then they're cold solder joints, and especially if they look cracked, then they're cold, then mechanically and electrically they're no longer good. So, question?
What size tip is that?
This is a, what size tip is this? I forgot what size tip this is. It's like a 0.5, I'll say like that's like 0.4 millimeter size tip. Generally for soldering, you want to scale your tip size to, you know, the size of the component that you're working with. You can get like, so depending upon the soldering iron you buy, certain vendors have like different kits or different tips that are recommended for different sizes already, size of components that you'd be working with as a recommendation. Really just the finer the tip you are, or that you're using, the finer the component you can work with. You will run into a potential bottleneck of not being able to deliver enough heat down the tip, especially if your component is just like on a big copper board that's just sinks the heat away, right? Then you'll have difficulty in delivering that heat to the component for soldering or desoldering. So for now, let's mock repairing this board. So let's say that we wanted to completely replace the replace the solder on this pad right here. So what we would need to do is desolder, and you can get desoldering braid, which what you do is you hold down the desoldering braid onto the part or soldering joint you want to desolder, and then you apply your soldering iron tip to that such that it will heat up the solder, it will melt, and then through capillary action, the solder itself will just flow into the copper braid. You don't really have to do anything for that. You can get solder suckers, which are basically just giant spring-loaded syringes. So once you heat up the joint, hit the syringe and make it pop, it'll just suck up the solder into it. But those are a little bulky, and sometimes they're not as easy to work with unless they're like electric desoldering solder suckers, which have like a vacuum to them, because the mechanical ones are a little hit or miss. But for now, let's desolder. I'm going to put this up on, that'll do, probably. That'll probably do. Okay. So I should probably have turned that on. Come on. There we go. Now it's turning on. Iron. There we go. Now we're at temp. Of course, depending upon the solder you're using, like leaded solder or lead-free solder, will determine what temperature that you need to set your soldering iron to. Get a digital temperature-controlled iron. Analog irons can work. They're just, it's nice to have feedback and a display of like what the temperature it actually is. So I applied the braid to the joint. Hello. And I think this one needs to be tinned first. Are you even on? Nope, there we go. Oh yeah, I didn't consider the smoke alarm. Oop, that's fine. All right, so anyways, now that the iron is tinned, so when you have a fresh tip, you need to tin it such that you get a little patina of solder on there, such that the heat flows better, and also that you can just start melting the solder that's already on the board. So let's go ahead and, so I've got the braid down on it, and it should just, come on. Any moment now. Are you actually coming up? Let's see. Let's just add more solder to it. Sometimes if a solder joint is so old that it's having difficulty to even get soldered, even desolder it, sometimes you may just have to add a little more solder to the joint to provide flux, which is kind of a cleaning agent and helps the solder adhere to and clean off whatever metal it's trying to adhere to. So now let's get more braid. Come on, come on. Okay. Well, that got rid of most of it. It didn't completely clear because sometimes you got to get around. So that'll do. Sometimes you really just got to work it some more, having it in a clamp and adding more solder and more soldering braid over time to completely clear it. But yeah, that's kind of the general overview and general gist for desoldering. So let's say that joint has been completely cleaned, and now we want to solder it back to fully repair it, or revitalize the joint, I guess. So now, heat up the joint with your iron, and then just bring in the solder. There we go. And then the solder will just flow right onto the joint. And now you have, a nice, clean, shiny soldering joint. There we go. Turn that off for the time being. Let's get back. Okay. So any questions on soldering, desoldering so far? Yes.
When you're desoldering, do you place the solder ring on top of the actual board, just next to
Between the iron and the joint. It just has to be between. Yeah. Yeah. Because I mean, sometimes I just like to bring the tip or the soldering iron tip on the side of a component instead of it being on the top. It's really just either way, as long as the braid is in, the desoldering braid is in between the tip and the joint, it'll heat up and pull all the solder out of it. Yep. Anybody else? Yes.
I just had a quick comment. You're working with a larger PCB, like a computer motherboard, for example. Sometimes you might have to actually preheat the board in order to be able to desolder components from it.
Yes. You can use like a hot plate for that.
Or even just like a hot air gun with that next.
Yeah, don't.
That's dangerous.
Yeah, you don't want to be taking like a heat gun, like something for like paint stripping. Don't do that.
Oh, yeah.
Because those are not temperature controlled and they just blast the heat out willy-nilly. You want to do like slow, methodical heat up passes to get the entire board not like melted, not up to that temperature, but just warmed up enough such that when you bring your iron in to heat up and desolder a little small bit of it, it doesn't just sink the heat elsewhere. Yep. Did you have a question? Okay. Is there anybody else who had a question? Yes.
For more complicated components that might have a lot of three-fold legs or something like that, what is a better way? I know I've used soldering tweezers for two components, but like other than just reflowing or hot air, is there a better way to like heat up multiple legs that are facing to each other?
Yeah.
Don't microwave
You,
the board.
yeah, don't make the bigger board. You can, with like a large enough tip, do like 2 pins at once and kind of do it staggered down the length of, like, say, a dip package or whatever. But really, you're going to be having to do it manual for each individual through-hole pin. Especially, and this is where you really want to get like a combination reflow desoldering gun that or station that's got the vacuum system to constantly suck up the solder while you're, yeah.
That's what I remembered I was going to say. If you're doing a very large project, I recommend getting at least 2 soldering irons, one big, one small, because you don't know what you're going to be working with unless you have like a full game plan of every single aspect.
Yes. Okay, turn that off. Cool. All right. There we go. Other common EE tools. Oh, we'll get into the probing later. No, we're getting into the probing now. Just kidding. Okay, so now that we've say that we finished probing, fixing the board, or really, this is just whenever you want to probe it. You don't have to probe it at any given time. Let's say that we want to check the voltage on this board, and this is just a demonstration of how to use a multimeter. Let me get to full screen. Full screen, full screen. There we go. So, say the board's repaired. It is. Get it operating. There we go. So, with multimeter, you've got your 2 probes, and then you've got the dial on your multimeter for all the different options. So you can do voltage. There we go. Voltage probing, and you can change that over to DC or AC voltage probing. Yes. There we go. That'll do. Is that better?
Yes.
Okay. So you've got voltage mode that you can measure DC and AC voltage, millivolts, DC and AC millivolts, and of course this is not volts. Volt measurements are universal to all multimeters, but some features are only unique to certain multimeters than others. So like frequency measurement, that's not always a standard feature on multimeters, but that's useful to have. Ohms, that's continuity measurement. So if you were to make sure just that you had a good soldering connection, so that's continuity test. But also resistance test, or that's diode test. There we go. That's capacitance check, or capacitance measurement, and this is resistance measurement. So say, let's do something common, which really most of the time when you're repairing electronics, you don't need to know how the circuit works. You can just see, I mean, you want to know how the circuit works to an extent, but you don't have to see the full schematics, right? Like if you can see that a battery wire coming to the board is broken and you resolder that, you want to make sure that the battery connection to the board is good. And the simplest thing of doing that is with a continuity measurement. So let's say that the battery holder itself we just repaired, right? And we wanted to make sure that the connection from the battery to the board is good. So I'm going to probe the positive side of the battery, and then I'm going to probe another point on the circuit that I know is positive. And I'm going to pick this big capacitor right here. So we know that just from the beep, we know that we have good connection there. Likewise, we can do like a voltage measurement and just make sure that the coin cell battery is fully charged. So for like these things, they're like 3 volts fully charged. So I'm going to probe from the top of the battery, positive side, and probe a negative connection. So we're getting like a reading of 2.94. So this battery is still mostly good. So really, when you're doing any sort of repair or debug work, you're going to be primarily using like voltage measurement and continuity checks most of the time, just to make sure that you've got good connection from your repairs. Okay, so let's swap back over to the slides. And turn that off. And turn. There we go. Rejoin at. There we go. So, answer.
You're saying you're afraid of damaging you're afraid of damaging the electronics with the testing probe.
Well, no, I'm sorry, not that, bro. When you do your soldering, I missed that part. Your soldering your joints, like, how do you make sure that you don't damage any of your
So, really, it's kind of used as little heat as possible. You don't want to just crank the temperature up to maximum is the first rule of thumb. But also, if you know the what part you're soldering, right, and you look at the data sheet for that part, some of them have like temperature charts of like, here's how long the heat should be, and that's really only for like reflow. But really, the main thing is practice. Find some scrap boards that you don't care about. Try practicing on them, and if you scorch something, that's fine. It's really just getting your own feel for it. Yeah. Yeah. Just do a live repair on your laptop while you're looking up the instructions for it. Yeah.
You will also probably be able to tell because like you can see a component frying.
Yes.
If you're heating it too much on the edge and it starts turning black and it's letting the smoke out, then
That, yeah.
If you're really afraid that there's one particular component that you're worried not just about being damaged electrically, but being damaged cosmetically, there are certain materials that you can shield it with. I've seen
Yep.
people use metallic materials, Teflon tape's a really popular thing for shielding things.
Aluminum duct tape.
Yep.
Yep. Copper tape.
People like
Aluminum foil.
conductive, so if you leave a piece in there, it doesn't explode.
Yeah. Yeah.
Another thing is if you have shaky hands, there are certain braces you can get for your hands to steady them better. As somebody who personally has hands that shake constantly, you do not want to have your hand suddenly jitter to the side and then cause damage to your components or your wires or yourself.
Yep.
So I recommend getting some kind of hand brace if you do struggle with shaky hands or nervous system anxiety or something of the sort. Also, remember to take healthy breaks.
Yes. So that depends upon the solder you're using. For leaded solder, that's going to be like 225, 230 Celsius, I think is the melting point generally. Because most components can only handle like 250 Celsius for a few seconds. But look to what solder you're actually using, and then it will actually tell you on the tin or on the data sheet, here's the actual melting point. Yeah. Anybody else? Questions? Okay. So, other common EE tools. So oscilloscopes, so instead of just instantaneous voltage or mostly voltage measurements with a multimeter, you can take voltage measurements over time with an oscilloscope.
And what's the use case for people?
So if you wanted to say see a clock signal, you want to make sure that not only you see the clock signal of the square wave going up and down, but also like the duty cycle, which is the amount of time that it's on versus when it's off, and Oodle's other characteristics like when it goes from, like, say it's a 5-volt system, and it goes from 0 volts to 5 volts on your square wave. You don't want to be seeing it when it goes to 5 volts when it's about to turn on. You don't want to see it like spike up to 7 volts, right? Or when it's going down from 5 volts to 0 volts on the opposite side of the square wave, you don't want to see it, spike down to a negative voltage. And that's like overshoot and undershoot. I'm going to give a demo of how we can use an oscilloscope in just a minute. So it's a virtual oscilloscope. I'm sorry. Yeah, I didn't want to pack my Rigol. So function generators, that's if you wanted to generate a signal itself, like a square wave or a sawtooth wave, sine wave, whatever, to inject like a test signal into something. Spectrum analyzers, so instead of plotting in the time domain a signal as it changes over time. So your x-axis on the oscilloscope is time, and your y-axis is usually volts, depending upon the probes you plug into it. What a spectrum analyzer does is say, think of receiving just broadcast FM, right? So radio transmissions, and you plug that into a spectrum analyzer. You'll get a waterfall chart of seeing like different spikes of radio energy at different frequencies. So from like left to right is lower frequencies to higher frequencies. Huh? Say again? Yes. Yeah. Yes.
Oh, electromagnetic. I thought
Yeah.
I was thinking of like actual just digital charge going through.
Well, you can still see that as well. Yeah, you'll still see a spectrum of frequencies. So say you send like, let's do a simple audio demo. Say you send like a 440 hertz, I think that's the A note. Say you just send that through as like a pure signal, right? If you plot from left to right, say like 0 hertz to like 1 kilohertz, and say that's a pure sine wave of 440 hertz, right? You'll see a single spike at 440 hertz of just that. But if you add in more frequencies to that, like say you add in 220 hertz below that, you'll see both the 440 hertz spike, but also to the left, because left to right, lower frequencies on the left, higher frequencies on the right, you'll see the 220 hertz spike. So it's really just, instead of visualizing your signals in the time domain, you're visualizing them from in the frequency domain as a waterfall spectra. Does that kind of help?
Yeah.
Okay. What's up?
So you're familiar with the spectrum analyzer? If you watch a lot of Ghost Hunting shows, they use it and they it's true.
Oh yes.
Yeah. They're weird. They're weird. Bench power supplies, that's the simplest of the bunch. That's just if you wanted to provide a programmable voltage with like current limiting, or if you wanted to take current measurements, say you're powering a board and you wanted to see how much current it's drawing while you're powering it, you use a bench power supply. Okay, so now it's time for the virtual oscilloscope demo. So let me copy that. Hello. There we go. And change over to display capture. Ooh. There we go. We good? We're good. Okay. So this is this is a combination of a function generator and a oscilloscope demo. So up here we've got frequency select and kind of what waveform you want to generate. So right now we're generating, I guess this is 10 hertz? Yeah, 10 hertz sine wave. And we're generating it at a 0 volt offset. There we go. So that way, and let's do something. Let's do it 0 based or 1 based. There we go. Okay. So this sine wave has a frequency of 10 hertz, and it has a amplitude of 2 volts per div, or not 2 volts per div, 2 volts, or 1 volt peak to peak. So with a 0 volt DC offset. So on the oscilloscope here, we've got a couple of dials for vertical position, horizontal position, the vertical divisions, and your time base. So, since this is a 10 hertz, because right now it's moving, it's propagating across the screen, and we want it to like stay put. So what we need to do to make sure that it's centered is set the trigger, which that's what the scope knows to when to start actually capturing. So we have a trigger level, which is just the threshold of saying, hey, scope, this is when you should start capturing. And since the threshold is still above the actual oscillation, we need to dial it down. There we go. So now as we dial down the threshold to 0, now the signal is staying put. And we can actually change the frequency as well. And as we change the frequency, you can see that because X is your time base, that'll just show more waves because it's a higher frequency for this given time base of 20 milliseconds. But we can lower the time base, and that'll just change how much of the signal is visible on screen at once. And we can also turn off and on the channel. Since this has a 0 volt DC offset, that means that it's just sitting right here on the 0 line, because this is your voltage axis, this is the vertical axis, and if we adjust the DC offset and increase, then we're moving the signal up as it's being shown on the oscilloscope, but it also just has a DC component to it. Anybody, any questions so far with this? Because this is like a whole subset of other things that once you start using it, it's again another skill that when you start to use it, you'll really pick up on it. So, good? Okay. So, back to the slides. No. Okay. Oof, I'm running short on time. Okay. Okay. Let's keep going. Hello?
Sometimes Google decides to freeze at times like this.
There we go. I'm just gonna skip. Oh, please don't crash. Okay. We're fine. There we go. Oh my goodness. Okay. So I'm gonna have to skip a few things, but we're gonna do a little bit of circuit analysis, and then we'll continue. So this little ConBadge itself, it has a mode on it where it will alternate blinking back and forth, and that's done with a 2-transistor LED multi-vibrator, which just does the alternating back and forth motion. So you see the 2 transistors on here and the LEDs. So what happens here is, I'm gonna have to skip the probing. I can show you all that later if you'd like. Is one of the, there's 2 legs here. So there's the resistors up here, then they charge these capacitors. And what happens is once the capacitor gets up to a certain voltage, this transistor turns on and it discharges the opposite capacitor. So that's how you get this back and forth behavior, is once you discharge one capacitor, the LED on the opposite leg turns on, and then it starts charging the opposite. Once this capacitor charges up, it turns on this transistor and discharges it, and then turns on the other LED. Okay, so yeah, this is able to be done because the capacitors themselves are, well, the circuit itself has small little differences in it, and if it was a perfect circuit, then it probably wouldn't start up, or ideal if like all the parts were equivalent. You have to have little bits of differences in them for it to kickstart itself and get going. Okay, so the overall formula for this is if you combine all the resistances together with the series and parallel formulas I showed earlier, you just take this formula of 1 over 1.38 times the total resistances in each leg times the individual capacitors here. and that gets you the blink frequency here. So I've set it in the schematic to be a couple of hertz. But that's only part of the story. We have to, because these are bipolar BJTs, we want to, and they're current controlled, we need to be mindful of how much these, or how big these resistors are, because the amount of current flowing into the BJTs is proportional to how much current they're allowing to flow through their collector pins, and thus the LEDs themselves. So that's why we have to look at the data sheets for these transistors, and they say that they have a gain of 200. So the amount of current that you put into their base pin, multiply that by 200-ish, and that will be the maximum amount of current you can have flowing through their collector pins. So for this example, the approximate equivalent resistance here in normal light, because these are light dependent, so in more light the resistance drops on these phototransistors, but in normal light levels that's equivalent to, like, with all that included, it's equivalent to like 15.7 kilo ohms of resistance. So we do this formula here where we know the battery voltage is 3 volts. We know the turn-on voltage of the BJTs is 0.7 volts. So 3 volts minus 0.7 volts, and then we're doing Ohm's law now, divided by approximately 15.7K, gives us about 1/4 of a milliamp. Now that we know that, that's the amount of current flowing into the BJT base pins. We multiply that by 200, and now that gives us about 29 milliamps of current that the BJT can actually source through itself. But since we want to keep the LED brightness nominal and not varying as much in different light levels, I opted to change the resistor on the diode leg, or the LED leg, to be a little bit higher, such that you limit the amount of current flowing through it. So instead of 29 milliamps, we're doing like 5 milliamps through the LEDs. And that's just something, if you look at the data sheets for the LEDs, which, as always, look at the data sheets, you can determine what the voltage drop across the LED is for a given current. So since we want to target about 5 milliamps of current flowing through it, we look at the data sheet, and they give you this little curve here. And at 5 milliamps, the voltage across it is about 2.5 volts. So since we have a 3-volt battery and a 2.5-volt LED, and we want to target for 5 milliamps, we do Ohm's law, and that gives us roughly a resistor about 100 ohms that we want to target for that. But due to like different variances, I opted to do a smaller resistor at 82 ohms to make the current more consistent flowing through the LEDs. Any questions so far in this current analysis? I know this is extremely glossed over. More analysis. What's up?
Oh yeah, when you were sort of deciding on the effect the LEDs would have when they were blinking, what's sort of the consideration for like persistence of vision or stuff like that? Because the components might hold on to voltage for a bit, like it might take the LED a second to dim, and so when you're designing the timing for that, like is it like FWA or like turning it on and off?
So that's just dependent upon the frequency that you set the oscillation to. For my circuit, or that sub-circuit, I opted to not have any persistence of vision. I still wanted to make the blink frequency noticeable, and that it's noticeable enough of a change in different light levels. And I can show you it later. But yeah. So now, how are we doing on time? 5:37. Ooh. How are we doing on frames? Okay. So I'm gonna have to skip that for now, but I can show you later. The instead of doing all that manually by hand, what you can use is circuit simulators like LT Spice or Falstad, and you can actually just draw up the circuit. There we go. Huh? I mean, it's still doing all the underlying physics. So it's not like digital logic, like 1 and 0. It's still doing it by continuous voltages. Is that what you meant by digital, or did you mean...
Like when you say simulator, I'm thinking like a simulator, like real world. Is it something, you know, is it accurate 100% of what you're actually doing?
It is pretty accurate. And that's also dependent upon like what models you feed into it. It's kind of like a garbage in, garbage out situation.
So is it very like technology? Is now it's more a algorithm that's kind of running the algorithm simulation, or does this go or does it previously code base based on the false? How is that?
I don't think it's going to be physical simulation. I think it really is just sort of, you know,
There's... Yes. Yes. This... Yeah, because this is purely just nodal analysis. Is that if you know all the voltages at each individual node at any given time, then, or well, you can find those, and then you can determine the actual behavior of the circuit. The mathematics for simulators are really well understood and really well, or match really well with real-world evidence and real-world experimentation. So they've been refined over the years to be pretty one-to-one. Yep. So, okay, let's get back to the PowerPoint. There we go. Okay. I'm going to skip these additional parts because they were covered in last year, but the circuit itself, it's got additional functions to it. For NFC, it's got a little NFC chip in it, so you can program to it. Yes. It's got a magnetometer for like a compass, so you can find north and south with it. It's got an LED ring on it for whatever pattern you want. An RGB LED, it's and then breakout pins, so you could plop it onto a breadboard and then use it as like a little programmable Arduino. It's got a microcontroller on it, which again, going back to the Arduino thing, and this is just whatever you want to program into it and have it behave is that's what you would do it. I'm going to skip those segments because this is just documenting how it works, but that's all listed on the GitHub as well. And the NFC is, if you want to program it, you can use phone app like NFC tools. And I mean, your badge that you got for FWA, that's a little NFC chip in it. So you can get like NFC tools on your phone and have it read off your badge. Do be careful though, and try not to brick your ConBadge. You kind of need that to get around.
So my understanding of the ConBadges is that they have a whitelisted database of serial numbers of individual NFC chip, and the data stored on the NFC chip is never used.
Yeah, it's
So
so
previous years, and I don't know, I haven't done this with my own this year, so your mileage may vary. I have to do it on this. This is okay with replacing them this year.
Yeah. Well,
with an NFC writing program, you should be able to do something like write your telegram to your contact and use that as a way to share numbers. If not, there are several vendors that I've seen that have like little bracelets that are dedicated.
So let's put a pin in that. But good to know. So here's kind of the overall process from designing boards from start to finish is step one, have an idea of what you want it to do, write up some goals and specifications of what you want it to do. Like battery life, what features it should do, what it should behave as. Part two is research what parts you want to use, what fulfill the needs that you're trying to go for. Simulate and prototype. Simulate and prototype again to make sure that it behaves as you expect it to before you actually start buying parts. Save yourself a lot of money by simulating first. And then additionally, you can prototype it on a solderless breadboard, which again, that's another level of testing you can do before you commit to the final board. Then you would draw up your schematic in a schematic software like KiCad, or really any other schematic software out there. There's oodles of them that are free and that you can pay for. So you would draw out your schematic, all your connections first, and once you feel your schematic is good and it makes sense, you think it works fine, you can move on to layout, which is then you're actually placing the components. You draw your board size, you're placing them individually where they should go on the board, and then you start drawing your copper connections between them. And additional information like silkscreen if you want to do like PCB art, or if you want to just tag the board with like your name or socials or whatever, you would do it in layout. After you feel your layout is good, you would go to a PCB fabrication service and check with their design rules, because you want to make sure that the board is manufacturable. For instance, you can go to Oshpark. They're a cheap and easy board house, and they provide a lot of tutorials and a lot of design rules of how to of what's manufacturable. So once you meet a board house's design rules, you can actually buy it, the boards through them, and build through them. Oh, I forgot that was in there. Cool. It's good. You can order your boards. So you order your boards, and if you don't want to assemble them yourself, you can also pay to have a service for them to assemble the components onto the boards. And that's fairly costly, but that's an option you can do. That's called turnkey assembly. So if you aren't doing that and you're going to assemble the boards yourselves, you would go buy your components through a reputable distributor like Adafruit or DigiKey, given a list of components that are in your design, or the bill of materials, or the BOM. Once you have your boards in hand and your components in hand, you would assemble them onto your boards, either by directly soldering them or putting like solder paste down and reflowing them. And you would actually just bake them if you were to reflow them. So 2019, I did a little like the balloons looking circuit, and I hand assembled those, and that was a lot for like 25 of those. So if you're doing a large order of boards that have many components on them, save yourself some trouble. Don't do what I did then and hand assemble them. Last year I was smart about it and just ordered my boards to be assembled as well, so that way it took out a heck of a lot of manual labor on my part. So bare boards are cheap, assembly is expensive. Bare boards, I spent for this 20 of these guys, that was maybe $100 or so in total. The assembly cost, that was pushing $1,200. And the reason for that, and this is why it's if I'm remembering, it was in the several hundreds of dollars, because you're paying for NRE, or non-renewable engineering, because they have to look at your board and have to figure out how to program the pick and place machines to put the components down. So there's like this whole lot of legwork that they have to do, and that's what you're really paying for if you're doing small quantity assemblies. This was done in China. Yeah. There's still a lot of U.S. companies that do this, but yeah.
I believe.
So.
Sorry.
Yeah.
I believe JLC PCB can make if you send them a pick and place file, it's a POM file with your board design.
Yes.
They feed that to their pick and pull machine.
Yep. That's no, that's industry standard.
Oh,
yeah. Yeah. No, the cost is really you're paying for the NRE. That's what you're paying for most up front, which is why it's so expensive up front. ITAR?
So, how do we go about, is there a way to be able to validate or confirm, like, hey, yes, you are the next phase, or actually also do this when you're trying to...
Ask if they're ITAR. ITAR. Basically, International Restriction on Trafficking of Arms or something like that. If you're doing something sensitive like that, you just ask if they're ITAR listed. Yep. So once you get your boards in hand, you want to test them, make sure they work. So this is what's known as board bring up. So these are photos from last year, where I went through on a Excel spreadsheet. I probed them, making sure that they powered up, making sure that the voltages on all the nodes that I probed at were what I expected them to be. Oh. Is it really that time? Oh, it's really that time. Okay. That was my reminder of, like, time is marching on. You'll get a kick out of the background. So, once the boards are tested and programmed, and they work, congratulations. You can now sell your boards. You can give them away as good as I did, or put them up open source. You should open source stuff. It's good. Put them up on GitHub. Do good. Open source your stuff. So additional topics that again, fractals upon fractals of subdisciplines. Amateur ham radio is another thing you can look into. Arduino, embedded programming, robotics, mechatronics. Bunch of recommended free software. So there's KiCad that I had mentioned beforehand, which is free and open source. LTSpice, Falstad simulator, circuit simulator, both good circuit simulators. Various scientific calculators. Of course, Arduino everything. And there's oodles of freeware out there for more EE adjacent stuff. Here's a good list of books, and ask me if you want some of these books. Yar har. That will get you more into electronics. So The Art of Electronics, that's kind of the Bible of electronics, because everybody and their dog recommends that.
That's a really high-level book.
Yes.
It's going to be for like more reference material if you're practicing EE. You try and learn it and use that book from the start, you're going to hate yourself.
A little bit.
Yeah.
Because I mean, there's other tutorials out there that are more beginner friendly, but that is kind of like the source. Of course, MIT OpenCourseWare. If you want to get a free college course on electronics and electrical engineering, look up MIT OpenCourseWare. It's free. It's probably one of the few free college things you can actually get. Wikipedia, of course, Wikipedia. Here's additional further readings. So Hackaday, of course, really good. MIT OpenCourseWare, allaboutcircuits.com, Adafruit, SparkFun, iFixit, YouTube, especially like Electroboom, EEV blog, bless EEV blog, not sponsored, love the multimeter, Great Scott, Ben Eater, Lewis. Hello? Yes. Or I'll send you the slides and the video recording. Yeah. Applied Science, Afrotech Mods, Mike's Electric Stuff, BigClive.com, Reddit. There's oodles of reference resources out there that you can look into and reference from. Starter kits. Look for starter kits. Those are extremely useful to get you going. Arduino, they sell a bunch of starter kits out there. Adafruit and SparkFun, they have starter kits that you can start learning from as well. Make sure you buy one with a tutorial or a guide to help you along, and instead of just flying blind, especially if you're very much a beginner. You don't have to read all of that. That's just a list of like recommended components that you should have in like your bug out kit of electronics and general lab supplies. So of course, soldering iron, multimeter, solder, iFixit kit, all the previous stuff I mentioned. EEV blog, he has a like $300 electronics lab video of like, here's the bare minimum that you should have. Contact info and Q&A. So here's all my contact info, and of course if you registered, I'll send all of this out along with the GitHub for last year's board if you want to make it yourself. You can contact me about any project you have, and I can give you free advice. I do not take commissions. I'm sorry, but advice is free, and engineering, random engineering questions, please nerd snipe me. I like getting nerd sniped. What? I'm gonna come back to you on that. I did promise you that. Okay. Thank you. So, as kind of a silly, I don't know if y'all noticed the background. So, 0. So, I don't know, maybe it's a generational thing. And because the music's relevant here too. Okay, question. Sorry, seriously, let's go. Yeah.
Sort of a comment for additional contact information. If you're specifically working on animatronic parts or LEDs and fursuits, you can reach out to me as well after now.
Yes, the electric fursuits is a good Telegram group. That's the one.
Yep. Really good Telegram group. Fun to help people.
Yep. Any other questions? Anybody? Depends upon what. That's a very open-ended question. What kind of work do you want to do?
I'm an electrical engineering senior, about to graduate in December.
Okay.
I have a specialization in control systems and signal processing, but I pretty much do everything across the entire spectrum. The problem is, I haven't been able to get an internship, and now I'm like scrambling, going, oh crap, what am I going to do?
Hobby projects.
Project that I need to work on.
Such as?
I have a
Like
suit
anything
that
audio electronics, making like visualizers and
yeah.
Hey everyone. So this is an addendum that I wanted to add to the FWA 2023 Intro to DIY Electronics panel because I realized that I was talking a lot about the electronics and the theory side, but it's a FurCon. I should have touched more on how to integrate this into fursuits and whatnot. I myself do not have a fursuit, however, I did make this tail. and I'm pretty skilled in sewing and electronics, so I think this can be a good example as a starting point for integrating electronics into your fursuit. So the tail itself is made from two separate fabrics, both from Mendel's. This back one is a long pile charcoal gray, and the inside one is a long pile lime green, and they just match my Sonus colors. And I patterned it out as a full lengthy tube. Of course, this is supposed to be a wolf tail, but it's not quite matching it. But for the sake of argument, let's just say it works. The seams themselves are on the inside of this, so I put the two furs face to face, stitched the edges and all the way around towards the end, and then pulled the two inside out, such that the actual fur is showing on the outside and the seams are well hidden on the inside. And then I filled it up with polyfill, and at the end I stitched on this little bit of fabric with these nylon straps, these nylon webbing straps, such that I could pass my belt loop through and hook it, mount it to my pants with my belt. The two straps are such that with shorts and pants that have the center back belt loop, you can align this and it'll self-align immediately to your lower back. Originally, this had EL wire in it, and what I learned then, when I originally made this in 2017, was that EL wire is simply not bright enough. Even in the darkest of dark rooms, it still barely gets through, mostly due to the long pile nature of this fur, but it's just not bright enough. So in 2018, I opted to upgrade this to an LED strip. So this is, I just got this RGB WS2812 flexible LED strip from Adafruit, and then just slowly fed it in to where the original EL wire was, all the way down the length of the tail on the inside. The popsicle stick itself is a fix that I did recently because this tail has seen quite a bit of use. So the after a while, the copper segments, copper interconnects, start to break down just due to the mechanical metal fatigue overall over time. So that's why the popsicle stick is there, and this soldering job is there to there we go, to just fix that. So this RGB LED filament is powered and driven over a couple of connectors, and these connectors are important. You do not want to have just soldered connections. So two connectors. One of them is passing the main power and ground through, and the other one is passing the data signal and a separate ground for strictly just the data signal. You can use any old connectors, provided that I think this tail draws about an amp or so at full blast, so this is 5 volts coming through. So they are being driven via a Arduino Metro Mini. You can use any old Arduino. Any Arduino equivalent or any programmable board that has WS2812 drivers on it will fit the bill. And that's just driving the LED strip and also sending power to it. The main power is just this 5-volt USB battery bank, and that's powering all the electronics and providing the main power to the LED strip. Separate control is through this Bluetooth module, and this is a Bluetooth low energy module that I got from Adafruit. Bluefruit UART module. So what it does is that I can control this over Bluetooth to my phone using an app like Bluetooth Serial Terminal, and I can just send it any commands to. So for instance, if I stop the random pattern, I've got 1 through 9 set up to show different patterns. So this. Oop, there we go. Speaking of metal fatigue, I may have to fix this one. There we go. Yeah, I'm gonna have to fix that too. Where I have different patterns programmed into it, so I can just send 1 through 9, and it will show different patterns, or do random, and it will just do random patterns on a loop. So that's how I'm controlling it over Bluetooth. The actual container for this is just a leftover pill bottle, and I find these are pretty useful if you can, provided you have the pockets for them. They're pretty useful that you can I just stick these in my cargo pants pocket, and the wire just feeds to my backside. So that's overall a good example of how you can integrate electronics into fursuits. There's oodles of other things that you can do. For instance, my partner made an animatronic tail using plans from Wolftronics, using a couple of servos to do pitch and yaw controls for their cattail. And you can put in cooling, you can put in sound effects. There's oodles of other things that you can do. So this is just an overall example of how you could implement electronics into your fursuit. Hi everyone. So this is a re-record of the FWA 2023 Intro to DIY Electronics Soldering segment and repair segment. Due to that part of the video, when I originally demonstrated it, I felt it was subpar. Probably just, it wasn't the best demonstration live, to be honest. So I decided to re-record it with all of the fixings and all of the good details for doing soldering, desoldering, repair, and all the equipment you may need if you choose to do this. So, to kick things off, we're going to mirror what we did in the FWA panel and do a mock repair of this FWA 2022 compass badge I made. But before we get started, let's go over the details of what equipment is what and what's its use for. So, starting out, of course, you will need a soldering iron. Really, any digitally temperature-controlled iron will do. You do not need a desoldering gun because those will scorch your boards, and butane torches and butane soldering irons are too much heat and not well controlled. So get yourself an electric, digitally temperature-controlled iron. I use a Heiko FX-888D iron, and this is just the tip. The main unit is over there, and it's a digitally controlled iron. Alternatively, for portable, I use a Pine-Sil soldering iron that is USB-C and barrel jack powered, so that way you can power it off a power bank on the go. Additionally, you'll need solder. So I've got a few examples here before me. So I've got normal tin lead 6040 solder. Of course, this is still leaded solder, so be aware of that and all the environmental details involved in that. Try and minimize it if you can. And then this is some lead-free solder. This is CQ100GE. So this is so far the best and easiest lead-free solder and, relatively speaking, cheapest lead-free solder that I've used so far. And that it flows and works just about the same as leaded solder, but is, well, lead-free, and thus better for the environment, better for your health. So on top of that, with the solders, you'll need fluxes, and what the fluxes will do is help the solder flow if it's not adhering, not flowing onto the parts or the pads of the board as well as it needs to be. So you can get syringes of flux. So there's different types, but it's best to start off with like no clean. And of course this is optional. This is only if you're doing like surface mount parts and you're having difficulty with the flux that's already built into these solders, because most of these solders, and they say it right here on the spools, this one is rosin core, and this one is, where is it? No clean, no clean flux core solder. So solders themselves will already have flux in them, but you can add additional flux to make things easier. So you can buy flux as a syringe that you simply squirt on, and you can get fine tips for these, which are extremely helpful when you're using narrow parts, really small fine pitch parts under the microscope. Or, and the cheaper option is flux pins, which are basically just little, you can think of them as markers. You just squeeze down, they're like little expo markers, and they deposit some solder. You can brush it on. This is good for larger parts. And again, there's different types of fluxes, so there's no clean, and then various types of fluxes that you have to clean off. And the best that I've found so far for flux cleaner is to buy dedicated electronics grade flux cleaner. You don't want to use store-bought like medical first aid grade isopropyl alcohol. And the reason being is that due to the contaminants in the water, you'll leave residue, like white residue on your boards, and it looks really ugly. It's a pain to clean off. So you're better off using proper flux cleaning, flux remover, like this stuff. And of course, again, this is optional. If you use no clean flux or no clean solder, you don't have to use flux remover. This is purely optional and only for fluxes that are like rosin core or fluxes that are not no clean. So this stuff is pretty good. Additional equipment, of course, deoxit. This is just for if you have loose connections, or not loose connections, but poor connections and poor connectors that are not making good contact. This will clean up those connections and make them more conductive again. So you can treat it just like WD-40 in operation. Just squirt it on, rotate the connector a little bit, or connect it, deconnect it a little bit, and it will, and you let it air dry, and then it will re-engage the connection if there's corrosion on it. What else? What else? What else? So there's two ways to desolder. Two primary ways. So there's flux braid, which you apply it while heating up the board, and the solder will wick onto the solder wick or solder braid. So that is one method. And another method is, of course, a solder sucker. So this is a plunger-style manual solder sucker. You heat up the solder and boop, hit the plunger and it'll suck up. Of course, you can get actual vacuum-style soldering, desoldering pumps that you don't have to do this constant action. And also the solder tip is built into the suction part of the device, so it's much easier to desolder. But of course, those are fairly expensive. What else? So, additionally for surface mount work, because sometimes even a fine tip iron is not enough, or if you have to deal with a part that has a large surface area that has many connections to the board, making it difficult to just individually one by one desolder a component or solder it down, you'll need a hot air reflow station. So this is basically a digitally temperature controlled and digitally airflow controlled hot air gun. So you got a fine tip that the hot air comes out, and you can control the temperature and you can control the airflow rate. So that way you heat up the part and you can desolder it or solder it down at a controlled rate, because you should not use heat guns because they will just scorch the part and they're not digitally temperature controlled. Additional tools, tweezers, of course, those are always useful. Wire cutters and wire snips, always useful. Wire strippers and wire cutters, very useful. And of course, needle nose pliers. And what else? What else? That's about it. Yeah, those are covering the main things. What else? Yeah, let's do the mock repair, and then I will show you a couple other additional things. So, this part right here, oh, of course, multimeter. Multimeters are extremely useful for fixing and probing your boards. So in this example, I'm going to set this multimeter right here, and we're going to set it to continuous mode, or continuity mode. There we go. So that's the beep indicates that there's electrical continuity. So the mock problem that I've demonstrated with this board is that let me zoom in. There we go. Is that the positive battery terminal for the coin cell battery holder on my compass board here is loose, and you can see it's lifting off the board. It's not making good connection. So much so that if I do a continuity check, see, I have to actually press it down to the board for it to get continuity, but otherwise it's not making good contact. So what we would do here is get any solder and just re-solder it down. Of course, my general policy is that if I am not selling boards to anyone, either inside the US or to Europe or wherever, if I'm not selling boards, I will use leaded solder sometimes. But if I'm selling boards or giving them away or sending them to Europe especially, use lead-free solder. So in this case, what I do is apply heat using the soldering iron. Make sure my tip is clean. Yeah, so if sometimes your soldering iron will get dark and grody and just dirty, and you can't conduct heat or flow solder onto it easily. So you can get these copper burnisher pads that you can scrub your iron tip into, and it'll make it nice and shiny. Additionally, you can get sponges that you would put some water on and, you know, hiss to clean the soldering iron. So now after you've cleaned it, you need to tin it. Just flowing some solder onto the tip, putting it back into the copper bristle pad again, and get a good tinning. So now we're going to heat up the pad, both the PCB pad and the component pad itself, and then flow solder onto both. There we go. And of course, make sure you're holding down the component with something that you don't mind getting hot. There you go. Make sure we're not short-circuiting anything. So that's a nice, good fillet. And you can tell it is by, loosen the board for a second. There we go. It's a nice, good solder fillet. And you can tell because it is not dull, it is shiny, it is consistent, there's no crumbling or fragments or anything, it's one solid piece. So, yep. Now we've got a nice, good mechanical and electrical connection. That connector is not going anywhere. And then let's do a continuity test and a functional test. So, grabbing the multimeter again. Yep, we're still good. Beep, beep. There we go. And I'm going to probe the board side system bus power, or V battery, and then probe the battery positive terminal itself. So we've got a good solid connection now, and that's not going anywhere. So that's a successful repair job. So now let's get the board powered up, and I can give you a visual functional test. So now once we insert the battery, there we go. Board's working again. So that's a visual example of how to do a quick solder repair job. So now let's talk about how this was assembled visually. So I've got a couple of revisions of the board before me, bare board themselves. So this was the first revision, and this was the follow-up revision that I gave away at FWA 2022. Only difference being is a little bit of copper changes, and also the silk screen being replaced with the finish being replaced with a gold ENIG finish for that nice color contrast. But either way, they still demonstrate the same thing. So how this was assembled was I grabbed the bare board themselves, and this was if I was manually assembling it myself, but for this board I did not. This I took, and the bare board manufacturer, I had them assemble the board as well. I sent the component kits to them, and they populated the board for me. So, as an example, because with the previous revision board, I assembled it myself. I bought a stencil that came with the board, and this exposes all of the pads. It's just a little metal bit of metal film. It exposes all the pads for all the components on there. And what I did, so let's take this away. Is mounted the board itself into a little board holder on my workbench here that kept the board still, and I could tape down the actual solder paste stencil and line it up with the board pads here, and then apply the solder paste. So here's a rough demonstration of how that happened. Is aligning the pads together. There we go. There we go. And it takes a little bit of finagling to do it. But once you've aligned all the pads, you would tape it all down and then apply solder paste to the board. And this comes in a syringe, or you can get it in little jars that you spread it on. And what I did is I laid down a bead of solder paste, and with a spreader of some kind, you can use any sort of card or whatever fits your fancy. And I'm going to just do this for the top couple pads for demonstration. Is spread the solder paste over like a squeegee, and if you get it right, and this is not the cleanest example, but you get the picture, is that the solder paste itself will only appear on the pads that you need to connect. And then you just, after all of the pads have had solder paste squeegeed onto them, you lift off the solder paste stencil, and that's when you start assembling, putting down components. So that's when I would, by tweezer, manually take each component and then place them down onto their pads with the solder mask, or not solder mask, sorry, solder paste, keeping them in place. Then, once all that's done, I would throw it into my PCB reflow oven, which is just a Controlio 3 kit. That it's basically just a toaster oven that is an aftermarket kit that digitally controls the temperature so that you can do precision solder paste reflow profiles. And once that's done, you are left with all the boards, or all the components soldered to the board. So that's a general example of how the board itself is assembled. Of course, if you didn't want to throw it into the, or couldn't throw it into a reflow oven because you don't have access, you would manually solder everything together, pin by pin, pad by pad, with soldering iron or hot air reflow gun. So that's the overall gist of soldering, desoldering, and probing and testing, and how this was assembled. So additional things are that if you want to reuse these solder paste stencils, which again you only need to use them really for surface mount components, you don't need them for through-hole components, you can rinse these off with IPA or rubbing alcohol, isopropyl alcohol, and it will clear off all the solder paste for them. I can't believe I forgot to mention this, but of course make sure you're strapped in with an ESD bracelet that is connected to earth ground, or any good access to earth ground, provided that your wall plugs are grounded. Make sure you're strapped in while soldering, desoldering, and working with electronics. Of course, obligatory mention for iFixit kits, as those are another essential tool for your electronics repair toolkit. Hi everyone. This is a re-record of the FWA 2023 Intro to DIY Electronics panel, the O-scope demo section of that panel, and I thought I would re-record it with a actual real oscilloscope in person instead of the virtual one I demonstrated during the panel. So the one that's before me is my Rigol DS1054Z. It's a fairly good entry-level scope. It's not the cheapest, but it is a pretty good entry-level scope. So, as I mentioned before in the panel, is that oscilloscopes, they display signals versus time. So your vertical axis is your voltage, and your horizontal axis is your time. When probing, oscilloscopes can have multiple probes to them. Sometimes it's just 2 channels, sometimes it's up to 4 channels, or even more on more expensive scopes. But the basics of the scope probes are still about the same. Is that you have your grounding clip, which you just connect to your ground of your circuit that you're probing. So this is to get a local ground reference. And your actual oscilloscope tip right here. Now, the oscilloscope you can actually just probe it like normal, or you can get little test hook caps that you would hook onto a circuit. Now, for sake of safety, the grounding clips are all connected to earth ground. So since this is connected to mains AC, the ground, the third prong, these are all connected to that. So don't try probing AC circuits like AC mains and connecting the this ground clip to any of the AC mains lines. Otherwise, you will certainly damage something. So, in terms of things to probe in front of me, if I can stop kicking my tripod, apologies. I have my DC power supply that's set to a constant 1.5 volts, and my computer that has its headphone jack broken out into left and right audio channels, which I will be generating signals from Audacity, and I'm going to provide a picture of what that looks like, what the physical circuit looks like connected up to it. And then also, here's just what's going on in Audacity, since you can generate your own signals on the fly, or different tones on the fly, different square wave, sine wave, sawtooth, etc. This is a good signal generator for our demonstration. So, I'm going to go ahead and probe the DC power supply, and it's set to a constant 1.5 volts. So, hooked on, and then turn on the probing. So, as a reminder, you have 2 main settings for your oscilloscope. You have your vertical voltage per division for each, that's set on a channel-by-channel basis, and your time base, which is seconds per division or anything smaller than that. So right now we're set to 1 volt per division, and we'll worry about the time base later, but 1 volt per division at 1.5 volts, and we can see that, well, 1 division, 2 division, there we go, or 1.5 divisions, we're at 1.5 volts. So that's just a constant signal. Now let's put in a AC waveform signal, and I'm going to be merging in the audio from Audacity so you can actually hear what that sounds like, because it is a audible frequency. So there we go. There we go. And now we've got a 400 hertz sine wave flowing throughout the headphone jack and flowing into the scope. So there's a couple of things that we need to do. One, we want to obviously look at this sine wave, but we need to try to fill it in, make sure it's taking up as much of the screen as possible, such that we can get a good reading, and also that it's not moving. It should be static, so that way we can actually analyze the signal correctly. So, since this is since it's so small, let's go ahead and turn up the scale, the vertical voltage scale. So we've got channel 1 selected, which is what the audio signal's on. And with this dial, you can actually change the voltage scale for that channel. And when you select different other channels, you change the voltage scale on them. So let's go ahead and raise this up. So now it's 500 millivolts per division, 200 millivolts per division, and going back and forth as an example. So now that we have the signal more or less fully taking up our screen, now we can change the time base. So right now it's set to 1 millisecond per division. So let's try to get the full division. So that's about a full waveform there. So since it's a 400 hertz sine wave, its period is about 2.5 milliseconds. So since we're at 200 microseconds per division, we can just count up how many divisions that is. So 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24. So 2,400 microseconds is the full frame. And since it's this 400 hertz sine wave has a period about 2.5 milliseconds, that's pretty close. So we're taking up about the full screen. So since it's an audio signal, it is also a AC signal. So you can see that it dips below the ground point, goes negative, and then dips above the ground point and goes positive. And also there's a DC offset to this. If this signal was truly AC, then we would be seeing it properly go above and below the 0 point or 0 volts symmetrically, but just because of the way of the circuit and the headphone jack's output, it's not fully symmetrical. So in addition to the scales, the two dials, this one is, as I showed earlier, the time-based dial to change your time base or seconds per division. You have two offset dials. So one of them changes your vertical offset on the fly, and that's on a channel-by-channel basis. So let's go ahead and just zero that back out again. There we go. And then there's also a horizontal offset. So we can actually change the offset in time such that we can move the signal left and right in time. But let's go ahead and center it back such that we're centered on it. Now, so far we've just been doing automatic triggering. So what that means is that the oscilloscope will just automatically keep capturing new data asynchronously with no matter whatever the signal is being inputted in. So we want to trigger on this signal. Say this signal was still moving around a lot, and we can still simulate that. But say it's still moving around. What we can do is we can change it to normal triggering, which all that does is it'll continuously capture whenever there's whenever it's passing the triggering criteria. So, and then there's also signal, which just captures a single scope shot, and you can manually do that up here with this single button. And then there's run stop, which starts capture, stops capture. But let's keep it on normal mode. And what we can do is change the trigger threshold. And what that does is that you can trigger off of various events when to start your capture. So right now we're setting our trigger to channel 1, which is the audio signal we're seeing before us. And let's say we want to trigger on a falling edge, so as the sine wave falls down. What we can do is change our slope to a falling edge, and there we go. And then change the actual threshold there we go. Let's say we want to change the threshold to be about 200 millivolts is when we change it, because that's about the midpoint on this sine wave. So there we go. So now we're triggering right up at 200 millivolts falling. So that covers the basics so far. Now, if we wanted to do further analysis of the signal, like, all right, we can clearly see it on the screen, but what's its amplitude? What's its frequency? What's all the quantifiable characteristics of the signal? Well, oscilloscopes provide measurement functions and cursor functions, but for now we'll just cover measurement functions. So you can say, hey, oscilloscope, give me the frequency of this signal. So go to measure, we select the channel we want to measure, and then for this Rigol, all your measurements are over here on the left side. So we select frequency, and there we go. It shows up our frequency there at the bottom, and it's showing 400 Hertz. Say we wanted to get the amplitude of this. Well, let's go over and get amplitude. And it's saying that the peak-to-peak amplitude of this sine wave is about 560 millivolts peak-to-peak. And we can also see what the offset, the DC offset is, by selecting VTOP. So that says it's about 410 millivolts off of the zero signal, and we can clearly see that with the 200 millivolts per division vertical scale, 200 and 400. So yeah, that's correct. We can also get the opposite if we want to see what the minimum is, negative 168, which is about right, as we're seeing on this signal as well, is that it's bottoming out to almost 200 millivolts. So that's correct. So this is just an example of all the different measurements you can do to quantify your signal. Additionally, say you wanted to save a snapshot of this to file. Most oscilloscopes, and it's kind of a recommendation nowadays, that you get an oscilloscope that has a USB port on it, so that way you can plug in a flash drive and you can actually save a snapshot of what you've captured and all the data surrounding that for later analysis. Additionally, if you're extra lucky, you can use your oscilloscope will have some sort of remote control function. For instance, my scope has an RJ45 Ethernet connection on the back, and I can actually, there we go, I can actually connect to it. Oop, there we go. sometimes it's a little laggy. There we go. Now I can actually both remotely control the oscilloscope and see what it's showing in near real time. But of course, nothing beats just working the dials manually yourself. So that's a general overview of how you use an oscilloscope. There's a few extra features that you can make use of. So you've probably noticed by now that I have two oscilloscopes connected up. One of them is connected to the right audio channel, as the label indicates, and the other one is connected to the left audio channel. Let's go back to auto. There we go. And let's set these two apart so that way we can see both signals at the same time. So this is where vertical offset comes in handy, so that way you can actually separate the signals so they're not overlapping each other. There we go. So now I'm going to turn on another 400 hertz cosine wave on the right audio or left audio channel. It's mirrored. So now both your ears should be hearing 400 hertz now. There we go. So now we can see two sine waves. One of them is cosine because it's just out of phase. And let's set the trigger properly. There we go. There we go. Make sure they're about even. Cool. So, as I mentioned earlier, oscilloscopes have alternate functions to them. And when you have two channels supplied to your oscilloscope, some oscilloscopes provide what's known as an XY mode. So instead of just plotting your signals over time in the x-axis and voltage in the y-axis, you can plot both of your voltages as x and y. And there we go. Nope. If I can find where it is. There we go, under menu for horizontal. So, since they're out of phase, that's important, because if I swap over to XY mode, now we're plotting a circle, because they're out of phase and their voltages are enough to plot this circle. But let's try to get the offset back such that it's center screen. There we go. And now we can add additional signals to this, such that we can make interesting patterns. And this is the kind of signals you would see out of, say, Jerobeam's oscilloscope music. So, if I add in some additional signals, like a sawtooth, actually separating it out, and the sine wave circles out to be almost a spiral. And you can go even further than this. So if I pause this, you can actually use something like Oscillo Studio, which is the software that Jerobeam wrote to create said music. There we go. So for instance, I modeled up this. It's the wolf emoji. It's just the wolf emoji is all it is. But I modeled that up as a 3D shape, and then brought it into Oscillo Studio, and had it generate a left-right audio signal that would create that pattern in oscilloscope XY mode. And then, as you will see before you, I recorded that as a output file that I can play back. And it generates exactly that. It's a little rough because this is a digital oscilloscope, not an analog oscilloscope, and thus all the quirks of CRTs, including afterglow and no digital pixelation noise that you're seeing here, would be completely absent. So we would actually be seeing the lines, the actual output lines, or the outline of this shape. So, yeah, that's pretty much all the basics of probing an oscilloscope.